So we use transfer functions to represent the dynamics or characteristics of a system in the frequency domain, whether it's a first order system like what you see here, or a second order system, or indeed any high order systems. The only thing that you need to know is that for any high order systems, we can consider them as a combination of number of first order and second order systems. So our focuses will tend to be on the first and second order systems, because once we know how to deal with first order and second order systems, and we can deal with high order systems as well, because we can break them down. Now, first order systems, we tend to use two standard formats. This is one of them. This is a very direct, simple way to define a first order system. And over here we have two constants here. A is known as the DC gain of the system. S is the frequency variable, so that's a variable there. T is a constant. It's known as the time constant. The DC gain is the ratio between the output and the input in steady state. So if your input is a constant, then the output in the steady state after the initial transitions, the output will equal to the DC gain times input. If DC gain is 1, then you have a unit gain system. Unit gain system means output will equal to input in steady state. Output equal to input, which also means there's no difference or no control error or no steady state error. So in many cases, we would like, not all, but in many cases, we would like the system to have a DC gain of 1, so that we know the output equals to input in the steady state. Time constant is a measure of how fast or how slow system responds to an input. Okay, so if we want a fast response, we tend to want a small time constant. If time constant is large, then the system response will be slow. Okay, so there are only two parameters, and it's in the form of A over 1 plus S times time constant. Okay, so make sure if you get a transfer function of a first order system, and in the denominator, if it is a 1 plus something S times a value, then this is in the standard form, number 1. Okay, for the first standard format, it has to be 1 plus something. So if that's not 1, this number is not 1, then it's not in the standard first format. And of course, you can actually reformat it. Okay, if they are not in the standard format, you can always change your format. For example, this one there, I have a GS equals to 20 over S plus 4. This is 1 plus, no, it's plus 4 plus S. So it's not in that first standard format. In fact, we will see later, this is actually in the second standard format, but it doesn't matter. Let's say I want to convert that into the standard format on this slide. Okay, so I divide 4 to the numerator and the denominator terms, as shown in equation number 2. So 20 divided by 4 give me 5. S divided by 4, that give me 0.25 S. 4 divided by 4, that give me 1 plus. Now I have 1 plus in the denominator. So once you get there, then what's on the top? That's your A. So I have a DC gain of 5. I have a time constant of 0.25 seconds. Okay, forget about that 10 there. This is just my page number, slide number. Okay, it got slightly mixed up. In fact, I'm going to just move it a little bit so we don't get confused. Okay, that's better. So that will give you a time constant of 0.25 and DC gain of 5. Okay. You can also, for any given transfer function, you can also find the DC gain by making all the s's to 0. Okay, so you end up with the DC gain. So in this transfer function, s equals to 0, you get 28 over 4, that's 5. In this transfer function, s equals to 0, this second term disappears, 5 over 1, that's 5. Okay, so DC means constant frequency, constant or zero frequency. So zero frequency, s equals to 0. But you can also have a second format, which is k over s plus alpha. Okay, now in the second format, the coefficient of s will be 1. Okay, if the coefficient of s is not 1, then that's not in the second standard format. Okay, and this is the first format, this is the second format. Now for the second format, if you have a transfer function in the second format, this alpha is known as the corner frequency, omega. There's an inverse relationship between alpha, the corner frequency, and time constant. Okay, so the time constant equals to 1 over alpha, or alpha equals to 1 over t. Okay, t is time constant. To find the DC gain from the equation 2, you just equate that s to 0. So DC gain equals to k over alpha. Okay, there's some interchangeable. They are interchangeable if you are reasonably comfortable with math. Okay, just it doesn't really take that much effort to do to change one format to another, or from this format to this one, or vice versa. Okay, but make sure. But what you need to notice is that when it's in the second format, this k is not the DC gain. Okay, because if I equate to s equal to 0, then it will be k over alpha would be your DC gain. Okay, so k is not DC gain. What's on the top? If we have something on the top, that is DC gain only if you have your transfer function in the standard first format. Okay, so that's first order system. Now, first order system, you can actually, the response you get out of standard first order system is something like that. Now, forget about the maths. What I'm giving you here is the blue line here is the input signal. So input jumps from 0 to 1 and then stays as 1. So you have a constant input value. That signal is known as the unit step. Okay, you can have also a step. Step doesn't have to be unit, but unit is 1, so therefore it jumps up by 1. It could be a step signal of 2, so it jumps to 2 and then keeps constant there. But in this case, it's a standard practice to use a unit step input when we analyze the behavior of a system. The output will typically follow an exponential function. It goes up and then settles down. It settles down eventually. So this is the entire transition period, but it will eventually settle down to a final value. Final value equals to the DC gain times the input. Okay, so DC gain times input, that's A times 1, that's 1. Okay, so that's really why DC gain is important, because we know from DC gain we can work out how much your output will reach. What will be your value for your final output value? Because if you know the input and you know the DC gain, you just multiply the two together. That will give you the final value. Okay, time constant has nothing to do with the final value, but it measures how long this transition period is, okay, before it gets to the final value. Okay, so the time constant is a time for the system to get to 63% of the final value. So this point there, okay, this will be 63%, or 0.63 times 8. And if you look at the time, this is how long it takes to get there. And obviously, if you have a small time constant, then this signal will rise up faster because 63% is there. Okay, it needs to get to 6%, 63% faster. If you have a larger time constant, then it will go up like that. Okay, it takes longer to get to 63%. So the two parameters of first order system, DC gain tells you about the steady state value, DC gain times the input. Time constant tells you how fast your system gets to the 63% of the final value. Okay, so you define the transition always follow a exponential function, as you can see in the yellow block on the top. So this block there, this is the general solution of a standard first order system. Okay, that's the output, the standard output format. Second order system is a little bit trickier. Okay, in that we will have a standard format like this. Okay, where the coefficient s squared in the denominator will be 1. Okay, so if your second order system is not given in that format, then you have to make sure the coefficient of s squared is 1. And we have three parameters in this case. We have a k, which is the DC gain. We have omega n, which is the natural frequency of a system. We have a zeta, called a damping ratio or damping factor. Now, there are different cases according to the value of the damping ratio. Okay, damping equal to 0, the system is undamped, means the response will have some sinusoidal, undamped sinusoidal. Damping value between 0 and 1 is what we normally discuss. Okay, between 0 and 1 is called underdamped, which will give you a pair of complex poles. Now the poles I will discuss in a minute. Okay, damping equals to 1. That's a critically damping system. That's where you have two real identical poles, as if you have two identical first order systems connected in series or in cascade form. Damping greater than 1, generally we don't really consider that as a real second order system, because they are really basically two first order systems connected together. The two different first order systems will have different time constants as well. So they are really, you can treat them as two first order systems. Now, dealing with first order system is easier than dealing with second order. So we will probably do that in most cases. Now I have an example here. The transfer function is given as gs here, s plus 4 over s squared plus 4s plus 16. Now if you compare that with s squared, the first thing you look is the coefficient of s squared. Okay, if you look at this standard format, coefficient of s squared is 1, coefficient of s squared in my transfer function is also 1. So the denominator terms is actually in the standard form. Don't worry about the actual s's on the top, okay? Because there are different possibilities. I can't list them all. To determine whether a transfer function in a second order system is in the standard format, you use the denominator terms, okay? And once that's in the standard format, you find the DC gain is easy to find. You just equate all the s's to 0. So s equal to 0, s equal to 0, s equal to 0, 4 over 16. That will give you 1 over 4, the DC gain. Okay, so the DC gain is actually very easy to find. And then you go to the denominator terms, because these denominator terms match the denominator terms in the standard format. So the first thing then you do is to compare the last term in your transfer function. The last term is omega n squared. Okay, 16 equal to omega n squared, therefore omega n equal to 4. And then finally, the coefficient of s in the denominator, the middle term, equals to 2 times damping factor times omega n. So 2 times damping factor omega n equals to 4 here. Therefore, zeta equals to 0.4. So it's actually not that difficult. So you find this again first, and you make sure your transfer function is in the standard format. And then in the denominator, you look at the last term, the number without s. Okay, this is omega n squared. So you find omega n from there. Once you found that, then you look at the middle term. The coefficient of s, in this case, is 4. 4 equals to 2 times zeta times omega n. Omega n you already worked out from the previous step. Therefore, you can work out zeta from here. Okay, so that's second order system. Now, the response of second system very much dependent on the damping value. Okay, damping high, very high. When you have damping of 2, that's where you have 2 first order systems. So you, as we know, first order system follow exponential functions. So you have, see here, this one is a very slow one. That's the exponential function, goes, settles down. Damping equals to 1. That's a still first order. That's just 2 identical first order systems, and it also follows the exponential function there. Now damping equals to 0.3. Now you can see, this is the third line there. You can see it goes over then the final value 1 there. It's go over slightly and then settles down. Damping equals to 0.4, you have this line. So you go over the final value, drops back, and then comes back to 1. And then damping of 0.4 is 2. That's this one. It wobbles a bit more. Damping equals to 0.1. It wobbles a lot more, but they will eventually, you can see the trend, it will eventually settles into 1 value. Okay? So some observation here. When the damping value is small, you will start, as the damping is reduced, you are starting to see some oscillations, but decaying oscillations in the system. Okay? The smaller the damping ratio, the more serious the oscillation will be, the longer it will take for the system to eventually settle down, or for the sine wave or oscillation to die away. But however, when damping is reduced, the response is faster, gets faster. You can see high damping, that's going up slowly. Reduce the damping, that goes up a bit faster. And then reduce the damping even further, it goes up even faster. So as you can see, this slope gets steep and steep as the damping is reduced. So the damping has a tendency of causing some oscillation problems. Okay, but it tends to increase the response, improve the response time. Okay, so that's second order system. Now, once we've done that, we actually looked at the zeros and the poles in your second year. Okay, so you have a general solution of zeros and you have a general form of transfer function like what we have here in equation number 1. If you equate the denominator terms, okay, what's in the denominator? Every term in the denominator, or everything in the denominator to 0, equate that to 0, that's your equation number 2. This equation is very important, okay? It's known as the characteristic equation of your GS, of the transfer function, or of the plant. The solutions or the roots of equation 2 are the poles. Okay? The poles of your system, these are. If you equate the numerator terms of the transfer function to 0, that's given equation number 3. The roots or the solutions of that equation will give you the zeros of the system. Okay? Zeros tend to indicate a response time improvement or deterioration, depending where the zeros are. But poles are a lot more important. It determines the stability of a system and the response time as well. But to find them, so I have a couple of examples here. To find the zero and the pole is fairly straightforward. For example, in G1, if I want to find the zero, s plus 3 equals to 0, solution will be s equal to minus 3. Therefore, I have 1, 0 equal to minus 3. If I want to find the pole, I equate the denominator term to 0, 2s plus 1 equal to 0. That will give me a pole of minus 0.5. Now, DC gain is also easy to find. Equate s, make s to 0, s make to 0, 3 divided by 1. So DC gain is 3. Now, this is in the denominator, I can see 1 plus something. It's in the standard first format for the first order system. Therefore, the coefficient of s is my time constant 2. Once I know the time constant 2, I can work out the corner frequency, which is 1 over 2. That's the inverse of time constant. Okay, so you can work out everything there. So you can work out the DC gain, the time constant, the corner frequency, the 0, and poles. For the second example, I have G2. And at this time, if I want to find 0, I can't. Because I cannot find any values, I cannot equate s to the numerator term to 0, because numerator is a constant. 4 can't be 0. So therefore, the 0 is not at 0, okay? So in this case, there is no 0. And I can find 2 poles. If I equate the denominator terms equal to 0, I have s minus 1, s minus 4, 2 poles. DC gain is also easy to find. Equate this s to 0, 4 divided by 4, that's DC gain. I can also find the time constants, because now these are actually expressed as 2 first order systems. And I can find the corner frequencies accordingly. Okay. Now, these two now expressed in a sort of standard second format for the first order systems, but we've done detailed discussions before in your second year, how to convert between them, and I covered a little bit of that as well early on. So we can find the values when we need to. Okay, so that's how to find 0 and the poles. Once we got 0 and the poles, one of the useful way to utilize the 0 and the poles is actually to put them in the S-plane. S-plane is basically the same as your complex plane. Okay, so we have real axis, have imaginary axis. If I have a 0 at z minus 1, and I'll put a little circle there to represent this as 0 of your system. If I have a pole at minus 4, and I'll put a cross there, that's minus 1, minus 2, minus 3, minus 4. So minus 4, that's a pole. So that's a real number. This is a real number. This is why they all sit on the real axis. And could I also have a pole on the right-hand side, that's s equal to positive 4. Again, that's a real number, so it sits on the real axis. But sometimes you get complex zeros or complex poles. For example, here, I have one complex pole at minus 2 plus j2. That's minus 2, so it's negative half of the real axis, but the positive imaginary number, so it's j2. And also I have a minus 2 minus j2, so The real part is the same as the first pole. The imaginary part is minus J2 instead of plus J2. Now, when you have complex poles, they tend to come in pairs like that. The real part is the same. The imaginary part will be 1 plus, 1 minus. Okay, it's called conjugate pairs. Okay, they come in that kind of pairs. Now, the location of the poles are very important because they indicate stability. Okay, this diagram shows if you want a system to be stable, then every single pole needs to be on the left-hand side of the complex plane. Okay, if you have any pole on the right-hand side, then your system is unstable. Okay, there's no if and buts. So any pole, even if you have 10 poles of a transfer function, you have 9 on the left-hand side, only 1 on the right-hand side, then your system will be unstable. Okay, so you want all of the poles. If they are real number, they have to be negative. If they are complex number, then the real part of the complex number must be negative. If you have poles sits on the imaginary axis, that's where there's no real part, just the imaginary part. Or your real part is 0. You have only imaginary part, then the system is known as the marginally stable system. Okay, it sits between unstable and stable regions. If a system is stable and you want fast response, then you want the poles to the left-hand side as far as you can. Okay, anywhere near getting close to the positive side, it's slow. Okay, or close to the imaginary axis. Any pole gets close to the imaginary axis, indicating that system, the response will be fairly slow. Okay. Now I've got some practical questions for you guys. There are two. Actually, I think there are 2 parts here, and really they are all something that you've done in your second year, or you should have done in your second year. And they're nothing too complicated. They are designed to help you to just to get used to what basically what helps you to sort of remember what you've done before. Next time, I'm going to do a revision again, but this time for a different reason. I'm going to do a revision on complex numbers. I know you should have covered that, you should have had that before in your math class or your math modules, whatever. But what I found from the past is that people tend to struggle with complex numbers. And unfortunately, for this part of your module, the control engineering part of your module, whether it's mechanical or aero, and we're going to deal with frequency responses, and to deal with that, we need to use complex numbers extensively. So I'm going to spend my next session on the revision for complex numbers. So really, I'm trying to kind of help you guys as much as I can, given the difficult situations we are now facing. Okay, thank you.